So last week we talked about optical coherence, in particular spatial and temporal coherence, right? And we were discussing the difference of passing a LED light through an interferometer versus a laser light through an interferometer. Yeah, and we talk about there can be fringes, but the visibility of the fringe could vary depending on the light source. Okay, so for example, this could be the laser, and this could be the LED. Yeah, all right. And remember, we give a description on the, so this is the intensity as a function of position. Okay, so this is position. So we give a formula, right? Remember, if you remember, it is like something like this. Yes? Okay, so just let me do it quickly again. I equal to the E squared, right? And E is E2. Sorry. E2 minus. So this is just a square, right? And then you have this, and if this is so if this is just complex, if this is complex notation, then you put a modulus around it. Yeah. So instead of bracket, you put modulus around it. Modulus, modulus, modulus. Yeah. And here you will have this. Remember? Okay, I hope you remember. And I said that this first term, they are just intensity, and they are DC signal. What is DC? DC is something that is just like almost like a background. This is DC. Okay. And this is the AC signal. AC signal is what fluctuates around this average background line. Okay, so DC is really like an average line, and AC is the signal that fluctuates around it. Yeah. Okay, and we said that this usually comes in the form of cosine kx, right? So that's a sinusoidal oscillation. Yeah. And we also said, so this is a little recap. We also said that if we put a parameter before it, okay, and use this to characterize the transition from if we add a parameter before this cross term or this interference term, and use this parameter to assign a value from 0 to 1 to this parameter, then we can use the set formula to describe the LED signal and the laser signal and everything in between, right? So I remember I told you that so we call this optical coherence. Optical coherence is not it's just a parameter that characterizes quantitatively how much interference ability your light source have. Okay, so in this sense, the coherent source and the incoherent source, they are not qualitatively different, but quantitatively different. And that quantitative difference is characterized by this thing, which we call the first order coherence function. Yeah. Okay. Now today we're gonna try to derive this formally, and in doing this, it will help us to see why why we want to talk about correlation. Okay? And this is a pretty straightforward derivation. I will just do it here. So again, starting from this formula, I have okay. Now, notice one thing. We know how this come about, right? Because this modulus is times this. Agree? Okay. So that's where this comes from. Okay. We notice one thing. First, this is a complex number. Right? Now, second, this is its complex conjugate. Yeah? Okay. So if you have a complex number and you add its complex conjugate to it, what do you have left? Huh? A real number. Okay? A real number. Specifically, you have the real part of this complex number. Yeah? So I'm just going to write, and that's 2 times. Okay? Follow me? Okay. Now, the next thing is we know that these are I1, I2. Yeah? So there's one thing we can do to make this look very much like this DC plus AC term. Okay? So a summation term plus a product term using the same notation. Okay? Now, this is how we're going to do it. Just put a square root so that the unit remain the same, right? So this will be a very natural form to have if we want to describe an AC term and a DC term. Sorry, this is DC, this is AC. Yep, okay. So now we have factored out this 2 square root. That means for this part, we're going to have just have this. Okay, pretty straightforward. Okay, we'll just factor out 2 real numbers. Yeah. Okay. All right, go. All right, so this is pretty straightforward. Okay. Now, in any real rate measurement, we are not taking one sampling point, but we take an average, right? So when you have a photo detector, we keep it on for continuously, and it collects data continuously, and what you see is a time averaged result. Okay, maybe a time average over 1 millisecond, maybe a time average over 1 microsecond. Anyhow, you're seeing a time average result depending on the device response time. Yeah. So yeah, so like I said, the device, before it can output a signal, it needs some time to process. The electronic circuit is sometimes the process, and during this time is keep collecting data. So whatever you do, any measurement result you get is an averaged result, time average result. So to make this real, because we were trying to compare with our formula with real situation, we needed to put time average around it. And that means this is time average. And this is time average. And this is time averaged. These are just numbers, so they can be factored out. Like everything is time averaged. Yep. Okay. Now, typically this is called instantaneous. And I mean, when I write this, these are all instantaneous. Yeah. And this is time averaged. Okay. But now just to make our notation simpler, I'm just gonna, because for all the I that we measure, it's always time averaged. So I'm just gonna drop this. I'm just gonna drop this time averaging for all the I. So I'm just gonna write this. Okay, but notice that this is time averaged. I'm just changing my notation a bit. Okay, but I'm gonna keep that. Still gonna keep that. All right. Yep. So if you compare this form, this equation to this equation, I think it's not hard to see that this is the coherence function that we're looking for. Okay? This is the coherence function we are looking for. Yeah? So I'm going to write here. Okay. And I'm going to change I to the same notation as E.
How did the time average of root I1 become I1?
This is just a change in notation.
No,
so here,
here
I1.
No, the root I1's time average become I1.
Where?
Yes. There's no square root.
Oh, I'm sorry. My bad. Thank you. Yeah. Okay. I'm simply dropping the bracket and make the notation easier. But this is time averaged. Okay. And this is instantaneous. All right. Cool. So Let me. Okay, let's see. All right, I'm gonna stick with this. All right. Okay. Now, so this form. So this form turns out to be very useful, as you will see. Okay, but first I want to explain what it is. The denominator, there are basically just normalization. So what is important is this part. Okay, so let me explain what this is. So this turns out will be very useful, and I want to explain what this is. Time average means yeah. So this is time average. Yeah, and maybe you put a t. So for the period of time of your averaging, you integrate it and you divide by t. Okay. Now, in the case of our interferometer, E1 or E2 are basically from the same bin. Remember? We have this, and then we use a bin splitter to divide it into E1 and E2. Okay, so they are from the same bin. And when E1 and E2 are recombined, let me just put it here, simpler. When E1 and E2 are recombined, in this setting, so this is bin splitter, this is mirror, this is mirror. In this setting, E1 and E2 are delayed by a path difference, right? E1 has a shorter time, it has a shorter travel path, and E2 has a longer one. So in this case, E1 and E2 are delayed, and E2 are basically the same as E1 because this is like a 50-50% equal bin splitter. So they are pretty much they're basically the same in every aspect, but E2 is a little bit delayed. So you can write it as this. Okay, so tau means this additional traveling path over c. That's the delay time. Okay, so they are basically from the same. So if I have a waveform like this, they are basically copies of this original waveform, but one is delayed from the other. Okay, so looking at this formula, for this case, we can write this okay, in this particular case, we can write it like this. Yeah? All right, so what this means is, I'm going to give a physical interpretation. So this form turns out mathematically is called convolution. Okay? Or autocorrelation. The reason why it is called auto means self. You're correlating something with itself. So that means you have a waveform like this, and you take a segment of it, okay, and you call this E1, yeah? And then you're taking, you're basically taking this segment and you displace it. Okay, and you call it E2. And there's a delay. Okay, so physically this is what we do, but mathematically this is what it means. You take a segment and you displace it. Okay, that's this. Okay, forget about this conjugate for now. Okay, just take them as real numbers. This is what it means. Okay. Now, so you shift it and then you and you add and you take a product of it and you average over. So this is time, right? You average, you take this 2 and you just, yeah, and you average over time. Okay. This is the mathematical operation. I'm not giving any interpretation to it yet. So I'm just explaining this is what this integral means. Okay. Yep. Give me a second. All right. Okay. So right now I'm going to talk a little bit about math. Okay. The general idea of correlation. So autocorrelation means you correlate something with itself, but just with a slight time delay. Okay. I'll explain it now. All right. So correlation, in general, the concept of correlation is, pay attention, is pattern recognition. Recognition. Is my spelling correct? Recognition. Correlation is meant to find pattern. Okay? Pattern in your signal. So if you have a signal that looks like this, okay? This is your signal A. Yeah? And this interval between this peak and dips are the same. You have one dip, 3 peaks, and followed by 1 dip. Suppose this is your pattern in your signal, okay? So you have just a signal. And so suppose this pattern is in your signal, but you don't know it. You don't know whether it exists, if your signal has a pattern or not, if your signal is completely random, or if your signal has some kind of pattern in it, then what do you do? You will make a full copy, okay? And you're allowed to change sign, or a partial copy. Either full copy or partial copy will suffice. Even a partial copy will suffice, okay? You make a copy of it. Let me just say, if this is a continuous string of signal and I open my detector only for a short time, suppose I catch this part. Yeah. And because suppose this is time 0, and because my measurement time is not synced with this, so I might have this signal shifted from its time 0. Okay, so my copied pattern looks like this. Oh, actually, you know what? Say because of some errors in my detection, I have the sign flipped. Yeah. So I take this segment. Okay. This remains, but one of the sign is flipped. Okay. So this is what I mean by a partial copy. Partial copy means not the whole pattern is taken, not the whole pattern is sampled, and even in your sampling, there's some kind of some error is introduced, and your sign is flipped. Okay, because of your instrument, whatever. Okay, I'll call this signal B. And this is T. And you see there's a certain delay between these two signal patterns. Okay. Now, can this be of any use? Even this, can this be of any use? Can we extract any information out of it? Well, let's see. Mathematically, correlation is to take these two copies together and sum over time. Okay, so that's what we're gonna do. Okay, so we're gonna take signal A and we're gonna take signal B. Yeah, and we're gonna sum over. And this delay is called tau. Okay, we're gonna sum over. Now this product give us a new trend, right? Here you have, so this is B. That's first. For the sake of simplicity of our discussion, let's normalize this. Let's normalize it. Sorry, let's shift this. Let's normalize it and shift it so that in our new scale, this becomes 0, and this is -1. Okay, this is -1, and this is 0. So we shift and normalize both signals respectively. This is -1 and this is +1. Okay, this will make our discussion easier. Yeah. All right. So let's see. So these are 0, -1, -1, 0, -1, 0, +1, 0, +1, 0, +1, 0, -1, 0. So that's how it goes. Now, when we take a when we make a product of it, okay, so maybe I should just write signal A and signal B product. So this is 0. So this is T0. We have everything 0, 0, 0. So the product is also 0 up to tau. Yeah. So this is tau. Everything is 0 up to tau. And for tau, oh, sorry. Let me just put tau 0. Let me just put tau 0. Yeah. For tau, you see tau is here. No. Okay. Let me make this easier. Let's say tau is, yeah, okay. Okay, whatever. Tau is an independent parameter, okay? And let me just say tau corresponds to this point. Yeah? Now, this is 0. This is -1. So your product is what? Still 0. Okay. So even at this point, it is still 0. And a little bit over, we have +1, but now it's correspond to this point, and that's 0, right? So you have 0, and this is T. So this interval is T. So this will correspond to this point. Yeah. So this is still 0, and this will be here, still 0. So everything is 0. Okay. Everything is 0. Great. So your time average of the two copies are 0. Yes? Okay? A segment, a partial copy. A copy from this region. Okay? So the thing here is, wait, let me just start over briefly. The thing is, there is some kind of pattern hidden in our signal. Or they might not be. They could be or might not be. How do you know? We don't know. Can we measure it? Yes, we can measure it. And the recipe, according to mathematicians, the recipe is you make a partial copy or complete copy. It depends on you. As long as you make a copy, a partial copy of it, so say like a segment, okay? You make a partial copy and make it into a second signal. And in this copying procedure, you're allowed to flip signs locally, not globally, but locally. If you want to flip the sign for all of them, that's fine too. But you have a lot of freedom. You copy this and you can shift it, and then you can do you can flip the signs. It's all fine. Okay. And the mathematicians told us if you take this new signal and the original signal and you take a product of it and you integrate it, something could happen. Something could happen. And we're not there yet. Okay? So I'm just giving you, okay, this is our first copy. Let me just put one because this is our first attempt. Okay? And so the mathematicians told us that if we take the product, make a copy and take a product of it with the original signal and sum over the entire trace, okay, that integral might be useful to us. Okay? Now, we have just done that, and we see the integral is 0. Okay? Not very useful so far. I mean 0. Yeah? But let's do let me wipe this out.
So here, if tau is multiple of t, then we will get a pattern.
Sorry?
If the tau is a multiple of the capital T, then we'll get a pattern.
Yeah, that's very clever. Okay, so this is kind of just a random tau, random shift that we choose. Let's do it again. Okay, let's do it again. Let's again make a copy, but this time the copy, we're still gonna take this segment, the same segment, okay? But this time we're gonna shift it to a little different position. Yeah? Let's say we shift it by the multiple of capital T. Okay? And let's say let's do 3T. Yep. Let's do 3T. So here, and I have tau 2. And now tau 2 is not random. Tau 2 is, because I don't want to get 0 again. I know if I choose a random value, it's likely to get 0 again because you want to, like after constructing this product trace, you know how this procedure goes, right? So let's try to do this a little more careful, and let's choose to have that shift to be a multiple of 2t. Okay. So that means I have this and this and this t. Yeah. Okay. So this is my second attempt. And again, according to the mathematicians, I need to make a product of signal A and signal C. And I need to see what it looks like. Okay. So again, this is so like I said, this is normalized 0. I have up to 2t, I have everything 0, right? So that's from here to here. Yeah, everything 0. So this is 0. Even though there are values, this is 0. So I know that this is gonna be 0. After, oh, sorry, no arrow. This is gonna be 0 after 2t. Okay. So that's like here. Yep. And then Oh, and then actually, just a little bit of before 2t it is 0. But now at this position, I have a -1, right? And here we have a +1. So what does that give us? That gives us -1 times +1. -1 plus times +1. How much is it? Come on, I need you to speak. +1 times -1. I'm just asking a simple question. +1 times -1. -1, right? Yeah. Let me just plot this here for you, so you can see it. It looks like this. Okay. So you see, it's 0. The product is 0 all the way up to this point, and then you have +1, you have -1. So you have a -1. You have a dip. Okay. And then it is 0, and then again, you have a -1, you have a +1, you have another dip. This is 3t. Yeah? And it is always, and for the rest of it, it's 0. Right? So great. So at least we have something that a boring flat line. Now what we do is we take an integral of this thing, of this curve. And what does that give us? Basically, I'm just gonna make it really simple. -2. I'm just taking this as a summation. -2, right? Okay. So you can play the same game over and over again. Okay? And then you can just take any signal. Let me just say S. I'm just put S here. And S is basically this partial A. Let me just take A prime, okay? This partial A times a delay, okay? So this is like a more general description of my B and my C, right? So I just take a segment of A, so it's A prime, and I shift it, yeah? And I take an integral, right? And then the value of this is heavily depends on my delay, as I just demonstrate. Yeah, so for every delay, you have a version of the signal. Okay, and then you just try different delay. You can do positive delay. You can do negative delay. However you want. And at some delay, you will see, like for example, when we have 0 delay. When we have 0 delay, do we have a signal? Yes. Our product is what?
1 and 0. 1 and
1 and -1. That's correct. Our signal is 0. Even though the pattern match, because the sign is different, so we have 0. Okay, but that's okay. And then we keep shifting it, right? And when we shift it positively by 1t, we have +2. So this is 1, this is 2. This is 0. We have positive 2. Oh, negative 2. Sorry, you're right. So this is 1t. Okay? So we have so I'm just put a cross here. Yeah? And okay, let me continue to do this. And if I shift in between 0, 0, 0, right? And then suddenly here are negative 2, right? And here 0. Yeah? So I have, so this is 0, 0, 0, 0, negative 2. And another one, 2t, I have negative 2, but in between I have 0. And here, 3t, I have, again, 0. Okay, so basically it looks like this. Yeah? And if I shift it really, really far, I have nothing but 0. It's all gonna be 0, 0, 0, 0. Yeah? If I do a minus delay, then as you can imagine, everything's gonna, if I do a minus delay, then everything's gonna be 0 until I hit t, right? Like this. And there I will have minus 1. Yeah? Oh, plus 1. Thank you. Yeah. Okay, thank you. I'll have plus 1. Yeah? And then continue. 0, 0, 0, 0, 0. All the way 0. So everything's 0. Okay? So this is this. Okay, let me just draw this again. 0, 0, 0. Okay, so this is our code.
40 you will have plus 1.
Sorry?
At 40 also you will have plus 1.
4t.
Yeah.
Okay, let me see. 0, 1, 2, 3, 4. Yes, you're correct. By 40, I will have plus 1. Okay. Okay, so you see? So this is t, 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 t. So this is 2t. This is 1t. This is 2t. Pretty symmetric, right? Anyway, you see, this is my correlation function. Correlation as a function of delay. That's called a correlation function. And if you have a non-zero signal, it doesn't have to be multiple peaks. Even just one peak will suffice. Okay? If you have just any non-zero signal coming up, that will be an indication that a pattern exists in your signal. Okay? So this is how correlation works. Correlation help you recognize whether there's a pattern or not in your signal. It does not tell you what the pattern looks like. It gives you a yes or no answer. If you have positive correlation, okay, or if you have negative correlation, that's all. It does not tell you what kind of the specific pattern that you have. It only tells you whether you have the correlation and whether it is positive correlation or negative correlation. Yeah?
So, but like you will also, if it's a non-correlated signal, random signal.
Yeah.
you will still have some places these things. So there should be some conditions like you will have repeating pattern or some symmetry.
Yeah, if I have, say, a noise, if I have a really noisy signal, right? Then you can imagine only at time 0, only without any delay, I will have maybe some signal. But again, oh yeah, I because it's like itself with itself, complete copy. So yeah, maybe I have like a dot here. But once I shift, even just a tiny bit, everything falls apart, right? So I go to 0, and everything goes to 0.
Randomly, you can have some.
But randomly, yes, you can have some peak and some. But see, this is an average.
Okay.
When you average, that's the beauty of it. When you average for a random signal, those fluctuations will be gone. Okay. So correlation is the tool that help us to recognize, to kind of detect whether there is a signal, a pattern in our signal. Okay. All right. Let's take a 5-minute break. Have some water, and we'll come back to Humphrey Brown. So that's, so we covered this. Okay, 5 minutes. Yeah.
In the experiment, like you say, like in the midterm, these slabs, but since I'm choosing the spin, I can choose any of these slabs, right?
Yeah, yes.
Like, so
Yes, of course. You're not doing optics now.
And when will be the first presentation?
The midterm week.
When is it?
When is it? I think it's probably at the beginning of May.
May.
Yeah, but I have to check the university calendar. Yeah, but there is like a midterm week. Yeah. If there's not, then it will be.
Within that time, the experiment will be.
Oh wait.
No, it's April. April.
Sorry. I was wrong. Not the midterm week. It will be the week when.
All
Wait.
the experiments finished.
Right. Yeah.
Stay in the group.
Yeah, like the switching week.
Just 3 more weeks because. No, 7.
Yeah, so
Yeah.
7 labs, so 5, including this week.
Yeah.
Today's Lab 3, right?
Yeah.
What is this?
For the book
Yeah.
already? Yeah. What did you think about it?
Well, kind of sweet ending.
Sweet ending?
Yeah.
Yeah. It's American also, right? Yeah. I like it.
Yeah, but sometimes I think like they figure out a solution, like they figure out the chain, right, to get it.
Oh, yeah.
But they linger on with manufacturing the whole thing. But I know the result already. Like that the the better the device almost always succeed and not fail.
Yeah, because it's a book, you mean like they can't fail because
No, because like when they come up with a solution, like we need to plug a circle.
yeah.
And they come up with a usage. And I'm still reading, but I want to skip to okay. I know you guys can do it, and you guys can do it.
Oh, this is okay. Can I ask you something about the last lab, Lab2?
Yeah.
So this is our data from the first objective. We do different.
Yeah.
So,
Correct. It's 301.
yeah, yes. So first we only have the main peak, like no splitting, and then we split it. So we have 301. You split it more with more current. That's reasonable, right?
Yes.
If like, we have more current, then the forces become more, so we get bigger splitting. So what I'm thinking about is, you see 3 different peaks. Do you also think this is of a different orientations of the center? Or?
So like there's objective 3, right?
Yeah, I have not plotted it, but
But that would just be that we will mainly use because also
because there is like
the most obvious peak will be the one we focus on.
yeah.
So like for your the 50 and the 248 will be the one we focus on. So it's like this one and this one.
I have the bigger one.
But this we didn't we won't focus on it, but it exists. But this is not a m plus 1 and minus 1 decision we're looking for.
So what is this?
This is another statement, but it's not considered in our simple model. I think.
Oh, you don't think it's just a different orientation of the crystal?
No. It's the original it's a more splitting state because we only consider Zeeman effects. Yes, we only consider Zeeman effects, but there's also more like amplifying or something just some other like consider relativity or stuff. So actually there will be more split.
Yeah.
So right now we only consider split, but actually it will have like
So I choose
nature
to
to
go
state
for
whether
the
some
presentation.
state
Yeah.
and it's a small.
But I thought it's like one was one of the peak, two was the second peak, and three was the
We're
first
not
peak.
decided yet.
And the explanation why would be this
We have
different
to
is
spin, we have to take
because.
either the.
But you don't think so, no?
Yeah, so I think
Yeah,
we will only see 2 pairs.
Yeah,
So like
Say
I will
one,
decide when I look
two,
at the lab and see what they are.
no. This is a pair and this is a pair.
How about you?
You mean,
Same.
So we will see.
yeah, you can show your
I think
your
it's
data also.
50% and talk
This is
about
objective 3, right? Yeah.
So focus on like 200 and 201, and here it is. Yeah, it's this thing.
There's two outer ones.
So okay, yeah. So there's also other people. You're correct. So this is the major we go.
Yeah, well, the big ones.
And there's
Outer ones.
other one.
And the smaller ones are where they want to double. Yeah, right?
Yeah, it's also
Yeah.
they will also increase by
Yeah, right.
by further.
But this is the different current.
Yeah, it's just 5.
Oh, you need more different levels, of course, to
Yeah.
get that resolution. Yeah.
I think that
I think it is only the first one. But then it gets
Oh,
really
they
bad.
want us to use 20 milliamps. So like,
Yeah.
so how many is it? 4 times? It will be 16
Yeah.
times. But we only do
You only say a few, yeah. Or you have to see the pattern.
Yeah.
But what's your
This is a simulated one. This is a simulated.
Yeah,
I
no, this
just,
one is simulated.
but
This
this
is
is the real data. So as you can see, like this
Yeah.
thing,
One more minute.
it's basically the same, but
that's basically this.
yeah.
And we only take a feedback.
But I'm not sure about.
But yes, this correlates to an angle, but I'm not sure how that angle relates to the real qubit phenomenon.
Because of what, like, if it's nearly aligned with the magnetic field, then the magnetic field wouldn't affect it so much. But if it's like orthogonal, it will be more. So that's why maybe V1 is higher compared to V1 because they are more aligned with the magnetic field.
Hey, but my understanding is that it's different energy states.
Could also be.
Not that's different energy state and not different because we didn't change our magnetic field. We didn't change our direction, we just changed the strength.
Maybe he wants to continue. We can continue talking in the last session. But yeah, I think that, I don't know for certain.
All right. So I want to make a summary. So in the autocorrelation measurement, so this is just like a general statement for a correlation measurement, right? In the autocorrelation measurement, you take the full copy. You take the full copy, okay? So instead of just a segment of it, you take the full thing, yeah? And of course they are still allowed to change its sign, it's fine. If you remain its sign, then you have positive correlation. If you change its sign, you have negative correlation. But you have correlation nevertheless, okay? So that's autocorrelation, a full copy, yeah? If you take a partial copy, or if you just take a completely different signal, and you want to compare the similarity between these two signals, okay? Then it's called cross correlation. This is a more general case. Autocorrelation is a special case of cross correlation, right? So E1 and E2. Okay. So here we have basically E1 and E1. E1T and E1T times the delay, and you correlate with itself. Cross correlation, you have E1T and E2T times some kind of delay. Yeah. And this E2 could be a partial copy of E1, or it could be a completely different thing. Okay. So if your correlation is non-zero, in terms of autocorrelation, if it's autocorrelation, that means you have a pattern exist. So that's the implication. A pattern exists in the signal. Yeah? A pattern exists in the signal of interest. Okay? If it's cross correlation, then that means, of course, a pattern, but even more, not only a pattern, but a similar pattern. A similar. How similar? Well, it depends on the correlation strength. Of course, the more similar the strength is higher, right? But this will basically at least indicate a similar pattern exists between the two signals. Yeah? Okay. So this is math. let's come back to the physics. Okay, let's come back to the physics. Remember earlier I gave you this. Sorry. Okay. Now, I think you can have appreciation of what this term is, right? Now, because E field oscillate, what's the average of the E field? 0. It oscillates around 0, right? So that this discussion that we just had, right? Treating the line as 0 shift, and then you normalize it to 1, right? That the shifting you don't need to do for E field, because the average is automatically 0, okay? But nevertheless, you still need to normalize it. This is the part that you normalized, okay? So this is really this. Okay? Yeah? So basically you have a field that goes like this, and a field that goes like this. So this is E1, this is E2, okay? And then you take the average. Okay, let me just take the average. You take the average intensity, so say like at this level. This is your average intensity. Yeah? And so say this is your average intensity. And you normalize it. Okay? You normalize your signal with your average intensity so that this becomes more like a 1. And this is -1, and this is -1, and this is 0. Okay? So this is what it means. So mathematically, this correlation function is what we just saw. Okay? This is the correlation function. Okay. Now, remember earlier I said this thing, I call this entire thing the first order correlation function, right? Okay, now I will just, for simplicity's sake, I want to add in a little more complexity. Okay, I want to redefine correlation function because we know that the E field does not only have a time chase, it also have a spatial pattern, right? It has like a beam pattern. and it has like a wave vector. Okay, can when it reaches this so if this is the detector, and when you reach the detector, it could go this direction and this direction, and they both hit the detector. Yeah. Okay. So this is K1, this is K2. Oh, okay. Or maybe I just call this K minus Kx, and this is positive Kx. Easier. Yeah, okay, sorry, I'm sorry. This should be minus because this is going down. This is positive. Okay. Okay, so when they hit the detector, this is detector. There could be a phase difference in addition to the delay. There could be a phase difference due to the spatial profile. Okay? So in general, in the case that we just saw, E2 is a copy. E2 was a copy of, it's almost it's the same copy as E1, but with a delay, right? In a even more general case, you will need to include the spatial profile, okay? Because we know that this is like a point, but that point has a phase, and that phase is determined by the wave vector, okay? So there could be, in principle, a phase, a global phase. That phase is independent of time, okay? That phase is added to the entire pattern, okay? And this phase often takes the form of KXX. Yeah? So, sorry. So this often takes the form of EKXX. Yeah?
In the case of an interferometer, is X the difference in pathway?
No, X is this. So if this is the camera, X is where you land on the camera.
Okay.
Okay. The path length difference is already taken care of by the tau, by the delay. Okay.
Yeah.
But on top of it, you can, that specific point that the wave arrive, they could come at a slight angle. Yeah. And there could be a phase like that. So here and here and here, they all have different phase. Okay. So so in the previous formula, we just kind of assume that they like the whole thing worked for one position on the detector. But now we want to make it more general. We want to include that they can hit at various position of the detector, and at each position, both will have a variation, or both have a difference of a global phase. And that global phase depends on the wave vector. Okay? So in light of this, you see that this formula here, normalization. Okay. Correlation is this part, as we have explained, right? But you can imagine the discussion will become more tedious if I didn't shift the average to 0, and if I didn't normalize it to 1 and -1, then we will have a lot of A0 plus some amplitude and B0 minus some amplitude. It would just become very tedious. So to simplify our discussion, I have made that shift of signal, and I normalize the signal to 1, so that our correlation curve looks, we can work with easier numbers, simple numbers for our correlation curve, right? that kind of correlation is called normalized correlation. So with the shifting, with the normalization, that is called a normalized correlation. If we just simply work with this, that is just straight, that's just straight correlation. Okay? And this number is not, since it's not normalized, so you can have a signal that is very big and a signal that is very small. And when you compare, you can still compare the pattern, the similarity, and all that, but the correlation you have, the absolute value of the correlation will depends on the initial intensity, the signal strength. And when you want to compare between, like, say you have signal A and you have signal B and C and D, you want to compare them, your correlation will have like very different value, and it's really difficult to compare how similar A and B compared to the similarity between A and C, you see? So a smarter way is before you do the correlation, you normalize and you shift your signal to 0, okay? So that when you do the correlation, when you compare the correlation, you can compare them under the same scale. And if the correlation is 0, that means there is no similarity. Very easy interpretation. If the correlation is positive, then it's right. And if it is +1 and +2, then you know the +2 have stronger correlation than +1. You can compare across different pairs. Okay, so that is just to standardize the correlation procedure, the comparison procedure, so that you can compare it between different signals. Here we're trying to do the same thing, but for the E field, like I said, the raw signal have already the 0. It's average at 0, so there is nothing to shift. So you don't need to worry about that. The only thing we need to do, otherwise you will need to like minus something. You need to shift it. But the only thing now we need to do is to normalize this to 1 and -1. And that is done by it's like the root mean square value of your signal. Okay? You just divide it by the root mean square value of your signal, and then this will be around 1, and this will be around -1. And working with its normalized signal give you a correlation that is easier for comparison. Okay, that's the purpose of it. And since this is already time average, you can be factored out of this. So we write them separately. But just know that this has no physical significance. This is just a mathematical convenience that allows us to compare stuff. Okay? Okay, got it? Okay, so let's rewrite this a little bit in light of this global phase. Okay, so here we have E1 T, E2. E2 is E1 tau times this, right? Okay, and when we take the value here, when we take the absolute value, the global phase goes away. The global phase goes away, so it is still, it is this. Yeah. And of course we have this here. Okay. Now, this is a constant in time, right? Like I said, this is a global phase imprint on the whole entire wave train. It is independent of time. It is a constant, so you can factor it out. Yeah. So rather we'll write like this. Okay. Yeah. So let me write it here. Yep. So now I will redefine this as my coherence function, first order coherence function. Yep. Okay. And you know, this is a complex number, this is a complex number. So in principle, this is a complex number, right? So if it's a complex number, we can write it like this. Okay, so a phase turn and an absolute value, right? Now, when we put it back to here, now we have, so here in this part, it becomes R1, gamma 1, yep. Okay. And now you take the, and since this is a real number, right? It can be factored out. So this thing, this whole thing becomes 2I1, 2I2. This plus real Yep. And this is just the cosine when we talk about, right? So in principle, your interference, okay, so this is it. So this is the entire, this is the complete, so the complete, your signal, your real signal is described by this. I1, I2 plus this. So this is the AC turn. This is the DC turn, and this is the AC turn. Okay? So you see this oscillation here? This oscillation depends on position. Okay, so that's what give you this that's what give you this wiggles. Okay? So that's let me draw this. So a general interference pattern looks like this. Okay? This is the DC part. And the DC part is I1, I2 plus I2. Okay? This is the AC part. And the AC part is 2 times this times this cosine. Yeah. Okay. And this is typically just kx, right? Okay, let me think. Is it 2 kx or 2? Yeah, I think it's kx times x. It is this. And this is the offset, fringe offset. Fringe offset. This shift the fringe. And this is the amplitude of the fringe. Okay? And this is the fringe periodicity. Yeah? So now the amplitude has an overall factor of this. So this determines how large is the fringe. Get it? Okay. So that's how that this is the most complete picture of interference pattern, optical interference. And typically, we measure the visibility by the highest and the lowest. So the peak and the dip. We measure the difference between the highest. So this is the difference. Okay, and we compare that to its. We kind of normalize it to its average. Yeah. So this is how we measure the visibility. How visible are your fringes? If your fringes visibility is 0, then you have only the DC part. And that will correspond to this is 0, right? So we can see that visibility, the measurement of visibility is related to the correlation function, the absolute value of the correlation function. And formally, people for simplicity, people call this correlation. Coherence function. First order coherence function. So instead of this complex version, instead of this, they call this the coherent first order coherence function. But it's just words. You know how this works. Now you know how this works. So you won't be confused by the textbook or the literature. Okay, let's do a little quick examination of this. What is the highest value this can achieve? Imax. Yeah. According to this formula. Okay, so this is DC plus AC, right? What's the highest? Huh?
Supposed to be 1 is maximum.
Let's use I. Okay. Huh?
I1 plus I2 plus 2 root I1 I2.
You see, this is a cosine function.
So next one.
So cosine can vary between 1 and minus 1, right? So the highest should be the cosine takes the value of 1. Yeah? And this is, of course, the highest. Okay, let's leave this out. Let's just say the highest possible, also included in this, the highest possible is I1 plus I2 plus 2 square root I1 I2, right? And this value, right? So that's the highest. What's the lowest? Minus, right? So let's do this. I1 I2 minus I2 okay, so here we have the same. This is plus. Okay. Yeah? All right. Now the moment of magic. So minus, this cancels. Yeah? Plus, but here we have minus opposite side, so this cancels. Yeah? So now we're left with 4 I1, I2, 2 I1 plus I2. Correct? Yeah? And of course, this is just 2, and this is just 1. So let me just write it easier. Okay? So you see, visibility is basically this part versus this part. Okay? This part versus this part. The ratio between this part and this part. And if you have full coherence, then you have this maximum value, maximum visibility. If you have zero coherence, this is zero, right? And in the case of, if you have, in our case, E1 and E2 have the same amplitude because you use a 50-50 beam splitter. In the case E1, in this case, then this reduced to I. So if this is I0, this is reduced to I0, and this is 2I0. Sorry. Okay? In the case of equal amplitude, visibility is a direct measure of the first whole coherence function, amplitude. Okay. All right, so this is the starting point of our next discussion on Henry-Brown experiment. Yeah, so hopefully I can finish it. So 5. Let's try to do this super fast. Okay, so Henry-Brown. Okay, so Henry-Brown Thisis, so HBT experiment. Interestingly, Henry-Brown is one person. Twist is another person. This is called Henry-Brown. Okay, so this is one person. For some reason, his last name has 2 words, and there's no dash in between them. So it's often confused. So sometimes people confuse this as 2 persons, Henry and Brown. But no, this is one person. Okay, and Henry-Brown's first name is Robert. So his name is Robert Henry-Brown. And this second guy, his name is Twist. His first name is Richard. Okay, so Richard Twist. Yeah, they are good friends, and at the time around 1960s, around this time, they were working on a problem. They're friends working. They're partners, working partners, colleagues, and they were working on a problem. And the problem is not physics. The problem is a problem in astronomy. Henry-Brown actually are not physicists. They are astronomers. Astronomers. I don't know if I spelled this correctly. No. And you? Okay. ASTRO and you. And you? ASTROAU.
Astronomer, so it's O. So it's not.
Come on. Okay, whatever. So they are astronomers. Okay, whatever. Okay, they're astronomers. They what they do is they look through the telescope.
Just said NO before it. Astronomer.
NO?
No, yes.
Okay. Okay, astronomer. Okay, so yeah. Okay, And so what they do is they look through the telescope and they measure the size of the stars. The size of the stars, for some reason, provide variable information for people who study stars. They can know a lot of things by their size. Yeah? And specifically, they are radio. Other than, like, besides the astronomy they do, they're more of radio engineers. Yeah. So this is what they do. Oh wait, previously we were in page board. I forgot. What was the number? Anybody remember?
5.
It was 5. Okay, thanks. So this is 6. So this is what they do. They look at stars and they measure the size of stars. And 9050, so between 9050 and 9060. The common method they use to measure the size of a star. Okay, well, first of all, we cannot really measure the size of a star because it's so far away, right? And even we can get there, like say we can get to the moon, we cannot measure the size of the moon because it's huge, right? So the best we can do is to use, instead of measuring its size, we measure its angular size, right? And if we can know the distance from the point of observation to the object, then we can calculate its size. So angular size is what people do at the time. Okay. Now, how do they actually around this time? How do they actually measure the size of the star? Well, first of all, they took the image. They used a telescope system and take the image from one point. Okay, so from one side of the star. So this part emits light in all directions. Okay, and then they take one beam. They take one beam here, and then take another beam here. Okay, and then they recombine them. To form an image. Okay. So of course there are like many beams. There are many beams. So you have enough beam from this point to form one image, and you have enough beam from the other path. Okay, let me use a different color. You have enough beam from another path to form a second image. Yeah? So what do you expect to see? You have two beams and you combine them. Well, this is very much like the double slit experiment, right? Here you have, it's almost like you have one slit here and you have one slit here. So these two mirrors are your slit that catch the beam. Okay, so let me just put like a slit here to indicate. So this is like a one slit, this is like a second slit. And this is the separation. Let me just call D. Yeah? So in a double slit experiment, we have fringes. Yes? and the fringe period is, let me see, is lambda over d. Anyway, yeah. Let me just use lambda over d, because this is actually an angle, but it doesn't matter. The fringe period is inversely proportional to the separation of the two mirrors. Yeah? The larger the mirror, the further separated the mirror, the smaller the fringes. Yeah? Okay. Now from the other side, they also do the same. They also do the same thing. They collect light here. To form an image, and it collect light here to form another image. Yeah. So these two are one set, and these two are other. So this belongs to A, and this belongs to B. A and B. Okay. So you have one set of fringes. You have a second set of fringes. Yes? Now, here is the point. You see, the two fringes are, the two sources are separated by some distance, and that distance is related to the angular size of the star. So that means these fringes will have also an offset. Will also have an offset. And this offset is related to the angular size of the star. Yes? Okay. Now, on your camera, you see both signals, right? You don't see them separately, you see both. Because you use the same mirror to collect this light from here and light from there, right? So on your screen, of course, this is a line cut. This is a line out of your screen is really like an image, but this is a line out. Okay? So in your line out, you have one set that goes like this, and this is A, and this is let me just call this X. Okay, so this is X. So this is from A, fringe A, and this is from fringe. Because the separation of these two mirrors are the same for both sources, so the periodicity are going to be the same. Yeah? So both are, let me just, here. Both are this. Okay? So now there is an offset. And this offset is related to the angular size. And your signal is the sum of both. Okay? So say if the offset is small, right? What do you see? The total signal will be, if the offset is if the offset is very small, your total signal will be this, right? But if the offset is large, how large? Well, if the offset is as large as the periodicity, right? So if the offset is as large as the periodicity, then you have a flat line. Why is that? No, they don't interfere. There are two sets of different signals. They don't interfere. This is 0. These are just two sets of sinusoidal pattern. Okay. But the reason they become 0 is because you have a pattern like this. You have bright, dark, bright, dark, bright, dark, bright, dark, and you have another set like this: bright, dark, bright, dark. Now you overlap them, right? If they are perfectly overlapped, since they have the same periodicity, you have bright, dark, doubly bright, and dark, bright, dark, bright, dark. But if you shift them enough so that the peak feel the dip, they all become bright, 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 everything bright. Okay? So by measuring the visibility, like we just discussed, by measuring the visibility, oh, by the way, in order to form fringes, we talk about spatial coherence, right? And this is chaotic light, thermal light. So another requirement for this to happen is that this needs to be small enough. The two mirror needs to be close enough within the spatial coherence of this thermal light. Okay, that's another requirement. Okay, but that's just another technical point. So if you measure the visibility, this is visibility max 1. Let me just say 1, and this is 0. Okay. So if you measure the visibility, then as a function of the angular separation, you will go like this, right? And this point is 1 over t. Okay? And then if you move it further, of course you'll come back. Right? So that's how this dependence is. However, we cannot change the angular size of the star, can we? Cannot, right? So instead, changing theta, we change our separation. And that will do the same thing, right? Because if you have a fixed separation, but now your periodicity is changed, at some point, the dip and the peak will line up. Okay, you can imagine that. Okay, so instead, people use this by changing D. People measure the visibility, and of course, they see the same thing. When this reaches the angular, let me just put this as theta 0. When this reaches theta 0, then the visibility is 0. And of course, when you keep going, it goes up. Okay, but let's ignore this part. So this is how people at that time measured the size of the star. They used an interferometer, and this is called a microsect interferometer. Okay, this is called a microsect interferometer. Now there's a problem with this interferometer because, as you can imagine, there's a lot of ambient disturbance, such as cloud, such as vibration of, if there's a truck coming back, your mirror vibrate, and your fringe shift, right? So this, you can imagine that this oscillates a lot. This could oscillate a lot, and not introduce a lot of errors. So in order to better narrow down the errors and find a precise value of 0 visibility so that you can identify this. Hambry-Brown was trying to figure out what will be a new way to do this. What will be a different way to do this? Okay, so one day when he was reclining at his chair at home, he had this idea. He noticed something. So he thought to himself, well, if I have a detector, let me see. Okay. So if I have a detector and the detector receives 2 light field, okay? The first field oscillate like this. So this is the first field, and the field has a certain frequency, omega 1, omega 0. Yeah. So he's starting from a completely different point of view, and he was thinking about light field, and because the detector cannot just receive, I mean, for the source he's working on, this is a non-monochromatic source. This has many different frequencies, right? So the detector will also receive another field that has different frequencies. So, and suppose that frequency is slightly different. Okay, slightly different from this light, from this first field. Okay, this is not a great drawing, but I'm trying to do my best. Suppose this light field has a different frequency, slightly different. Okay, you know they are gonna the periodicity will vary a little bit. Yes, but the cool thing about this is, at first when they coincide, if there is a coincidence point, so say like here, at some point later there will be another coincidence point, and the periodicity and the time it takes for the coincidence to occur again is 1 over omega 1 minus omega 2. So sorry, 2 pi over omega 1 minus omega 2, which is the difference frequency. Okay. In electrical engineering, this is called the beat frequency. The beat. If you have two signals that have very similar frequency, then you put them together, then they will create a pattern that looks like this. They will create a signal that looks like pick, 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 pick. And the closer they are, the longer the beat occurred. Okay. So anyway, so you can imagine that the interference. So if you take, so again, I equal to I1, I2 plus right? So if you take this product, you will, if you take this product, you will see that here you have overlap. So that's the time, the product. Okay, so real. If you take the product, you'll see when they overlap, they create a strong pulse and a strong pulse. Yeah. So just give me a second. And when you take, so instead of okay. So instead of combining the two beams, if you just take one, if you just take the intensity, wait. Huh. Give me a second. This should be, sorry. Okay. Let me just do this. Okay. Okay. So instead of looking at the image from this start, right? He decided to take the intensity of this light field, collect the intensity of this light field. And here you have this beep and this beep, right? Oh, sorry. That was after, sorry. This is, so that's here. You have this beep, just like I drew there, right? And for the other one, sorry, the second detector, take the same signal from another source, okay? And then you do a correlation. You correlate them. So this is IA. Oh, sorry. This is signal A. This is signal A, and this is signal B. You correlate them. Turns out, so this is signal A, and this is signal B. You correlate them, okay? Turns out the delay, as you can imagine, the delay will have to do with the angular size. The delay will have to do with the angular size. Yeah. So if you take the correlation scan, you take one. So this is like cross correlation. You take this signal and then you scan. You also take this, but you scan through it. Yeah. Then let's see. That's some. Okay, what I try to say, I'm sorry. What I try to say is a certain delay, the correlation signal will drop to 0. And sorry, this is not proportional. They are just related, but not proportional. Okay, so somehow it's related, but not proportional. At some point, it will drop to 0, just very similar to the visibility measurement. Now, since he is working, this tau is controlled by, again, the delay, the separation between. So this correlator is basically a multiplier, okay, and the delay is controlled by the separation of the two detectors. Okay, so at some delay, you'll hit a value, and the correlation will drop to 0. Okay, and because this is a thermal light, and by that time there is already known through this signal relation. Signal relation says that the correlation of a thermal light, so this is only applied to thermal light or chaotic light, thermal or chaotic light. This is related to the visibility by this relationship. So if you know the curve of C, when C drops to 0, you know when V will drop to 0. Yeah. Okay. So this is basically so if you see, sorry, this is not 0. This is 1. You drop to 1. You'll drop to 1. Okay, 1. And since this is intensity, earlier we talked about correlation between E field, right? And 0 correlation means no correlation, no patterns, similarity. But since this is intensity, intensity has the average value of intensity is not, if you have like a fluctuating intensity, the average value is never 0, right? The average value is like something. So if you, after you normalize the average value, your average, your standard zero position is 1. Okay, so for intensity correlation, okay, so here he's measuring intensity. So S here now means there are not E field, but the signal here is intensity because you are using a detector. So this is intensity. This is intensity. Okay. And so for intensity, 1 means no correlation. Yeah, 1 means no correlation. And I can derive it, but I don't want to waste time doing that. So I'm just saying that the correlation will drop to 1 at after some delay. And because of this relation, see, you shift this. V is basically C01 take the square root. Okay? So if this is like a Gaussian or an exponential, let's just say this is a Gaussian. Okay? For just easier. If this is a Gaussian, okay? And it has both, you can do positive and negative delay. Then you shift this down. So this is Gaussian plus. You shift this down, and then you take the square root, and that becomes this. Okay? So this is the visibility curve. Visibility curve. And the width of this will tell you the size of the angular size of the star. So instead of measuring the visibility through an interference pattern, you obtain the visibility through a correlation measurement. And this is, the intensity is more robust. Even when you have like phase disturbance or a cloud or like anything that disturb your phase, it will not affect your intensity. Okay? So this is a more robust way of measuring, of obtaining the visibility and measuring the angular size of the star. Okay? Yeah, so right. Okay, let me see. Let me just I just want to write this down without explaining it, but I just want to show you that it is the normalized I is indeed, the uncorrelated I is indeed 1. Okay. This will be quick. So IA, IB, yeah? Okay, so try to follow. So IA is this, and it has like a certain offset. IB is this, it has a certain offset. Okay, so we are gonna put this, decompose IA into the offset plus its fluctuation. Okay, its pattern. Okay, let's call it signal A. Okay, and we do the same for IB, signal B. Okay, so you see the product is, sorry, I0, A0. So that's this. B0 is A0, SB. Okay, SB. So this is basically the experiment, the example that we were doing earlier, right? Like formally it is written out like this. Now when you do a time average, which is integral, when you do an integral, then that does this, right? Now A and B are constant, right? So they just come out on the integration. Sorry. A, B, B, S, A, T, A, S, B, T. S, A, T, S, B, T. Yeah. Now, the average of SA and SB, because this is SA. This part, this oscillation part is SA. This oscillation part, this fluctuation part is SB, right? The average is 0. Yes? So this goes away. 0, 0. You have this left. Yeah, okay. So now if you normalize this whole thing, right? You normalize it with the average intensity. Yeah, you normalize signal A with average intensity. You normalize signal B with average intensity, right? What does that give you? It gives you this. 1 SA, SB, and B. Okay? Right? So this is the normalized correlation function that we talk about. Yeah? So this is the part that has the real signal. But you see the offset is 1. So when there's no correlation, when the correlation is equal to 0, if we call this the correlation function, then it will take the value of 1 for the case of uncorrelated signal or no pattern signal. Yeah? Okay, so that's why the Humphrey-Brown experiment, the signal looks like this. Okay? And you need to know that but fundamentally this has no limit. This could be large, very large. Okay? Or small. right? Or small. So let's see. So classical, I'm sorry. Oh, sorry. This has to be this has to be positive. Okay, this has to be positive. Okay, what I'm trying to say is this this correlation signal, this intensity correlation signal. Okay, let me just call it. Oh yeah. You see, this has the same form. This has basically the same form as we had previously for the E, right? But this now instead of E field, we have the intensity, which is the square of E. So in this case, this is called the second order correlation function. Okay. And the second order correlation function, as you see, it is sorry. The second order correlation function is larger than 1 and smaller than, and there's no upper bound. Okay. So this is from the classical wave or classical coherence theory. You can derive this. Okay. So this is okay. So this is the basic tools. The intensity correlation is the basic tools that we're gonna use for our optics experiment. And what is very funny, what is kind of funny is when they invent this method to measure the angular size, it was just purely an engineering problem. They had no, they did not have any physics or optics in mind. They're not thinking about that. But later people used the same, physicists, they used the same experimental setup and apply to optical measurements. And they found like all kinds of very interesting things. And they realized that the coherence function, the second order coherence function can be used to distinguish photon distribution. We will cover that in a later lecture. So therefore you can distinguish between the so-called classical light source and a non-classical light source. Classical light source will always satisfy classical coherent theory. So the second order correlation is always larger than 1. But a non-classical source could have, for example, single photon source could have coherence smaller than 1. And that's one of our labs try to show, the Hong-Ou-Mandel experiment. Okay? So I'm just saying that it turns out that this tool that developed to solve an engineering problem turns out to be a remarkable, very resourceful tool for physicists. And this is like the starting point, becomes starting point of quantum optics experiment. Yeah?
But we haven't talked about it.
We haven't talked about it. But I just want to tell you that this is the significance of it. And that's why our quantum optics lab is using this measurement, this type of measurement for our single photon stuff. Yep. All right. So that will be all for today's lecture. And before we proceed with the quiz, I want to just show you Humbert-Brown's interferometer. They call this intensity interferometer. But really, there's nothing interfering. Yeah, they're just doing pattern recognition. So wait. Okay, it shut off by itself. Okay, this is the Humbert-Brown. This is the Humbert-Brown experiment. It's actually very, very large, huge. Here we have. So these two are the mirrors that collects the light. Except that here they are not collecting visible light. They're collecting radio waves, electromagnetic wave. But the concept is the same. And this circle is where this circle is a rail, circular rail, and you can see that the two. I wonder if there is a stick. Oh, I'm just going to use this. You can see that there are two. So there's two mirrors. There's two. Yeah, I guess you can call them mirrors. These two mirrors are here, and this is these are the detectors. So they focus the light to the detector. Okay, they focus the light to the detector, and the spatial separation can be varied by moving on this circular rail symmetrically. Yeah. So when you're doing the measurement, you can bring them really, really close, or very, very far apart. Okay, and when you're done with the experiment, they are put into the garage here. This is the garage. And this is the control center, which you can see it as the correlator, the multiplier. So the delay is controlled by the separation of the two mirrors, the two giant mirrors, and the multiplication, the correlator is done here in this house. Yeah. So this is the Humbert-Brown experiment. It's pretty significant, pretty big. All right. So I just want to give you an idea. Yeah, that's in the 60s. Okay. Oh gosh. Okay, we are a bit over time, so we're gonna do our quiz pretty fast. Can you help me turn this off? Thank you. Thanks. Don't worry, the quiz is relatively simple. Quiz 1. Was single-photon detected in the original HBT experiment? Okay, so that's the first question. The second question is, in HBT, intensity interferometer, they call this intensity interferometer. The thing I just showed you. Does intensity of different light field interfere with each other? Okay. So for the first question, yes and no. Okay, let's save some time. So come up, and you know what to do. Phoenix? Okay, so everybody choose no. All right. All right. Let's spend 2 minutes and discuss with each other. You three will be a group, and you two will talk. And try to challenge each other's answer. Justify your answer, and the other person challenges it. Okay.
What did it show? There's photon, but there's light. There's no idea of photon. What we talk about still waves. Understanding that's wave interfering, not a single.
So radio waves are photon.
In the detector, you mean, or?
Yeah. It's just we dictated intensity, and the intensity is the interference of the correlation of the waves.
What did you just
not how many? Yeah, it's not a single photon. It's just how many photons is a larger amount of photons, and how's the amount difference.
It's the average use thing.
Yeah.
You would not be able to use it. You would not be able to see this technically.
Probably yes. And it's not a yes or no. It's a how many, or is it more or less. And also, I think even till today, single photon detection needs to be like superconductor or something.
I think you can do it now, but it's not probably not what they did like refers
like
but you said it's about correlation, right? So you're looking at average. I don't know how to challenge your answer.
Yeah.
It's talking about the original experiment.
I don't know how the real what the lab is doing. What is it? Very I don't know.
Well, this might be a trivial question given the lecture I just gave, but just know that we are using the HBT setup for our single photon experiment in the lab. Okay, so that's why I'm asking this question. When they were doing their experiment, did they detect a single photon? You see what I'm saying? Because we're using their setup in our optics lab to detect single photon. Okay? So in their experiment, did they detect single photon? That's the reason why I'm asking this question. Okay.
Yeah, I agree with you.
All right. So let's get back to your line. Do we have anybody who wants to change side? Understand? Are you sure? All right. To save some time, we will not proceed with the second round. Yes. The answer is yes. The reason is that the correlation they measure is larger than 1. For quantum light, which single photon is quantum light, it need to be smaller than 1. Smaller than 1 is the quantum region. Larger than 1 is the classical region. Okay, that's the reason. And their measurement shows it's larger than 1. Okay. All right. So for the second question, so this is everybody. So for the second question, in HBT intensity interferometer, that's what they call it, right? Does intensity of different light field interfere with each other? I mean, it's interferometer. It's called interferometer. So anything is interfering. Does the intensity of the light field, different light fields, interfere with each other? Okay. So let's see if, pick your line. So David and Simon and Peter and Phoenix and
What do you mean by different light fields?
It could be the light field collected by the same detector or the light field collected by different detector. Doesn't matter. I'm just saying it. Do you think there are different light field, the intensity of different light field interference? I mean, because it's called intensity interferometer, right? So by its name, it's easier. It's very easy to get an impression of maybe the intensity, some kind of intensity. The intensity of something are interfering. Okay, so I'm asking that question out loud, and then you can give your opinion. Okay, anybody want to join him? You want to stay in your line? Okay, all right. Everyone make a decision. All right. So I will have you talk with Musfa, and then you three will discuss. Phoenix and David and Vida.
I think when they say it's a more accurate or
Isn't
narrow
doesn't that
definition of
correlation
it,
show up
because like
due to
because
the
they
interference?
separate it into the whole I is for the SA and the one that varied. So there's a baseline and the one that varied, and the baseline. So and when we like do the formula, the baseline always
Oh yeah, so it's
there's
we are looking at
the baseline and the variation.
actually making
And what they're interfering is the variation part, and the baseline is always solved.
Yeah, because you're not like mixing the
Variation is always zero.
Looking at the correlation.
you can see your
Just in the four terms.
You don't follow me. How does like this?
Contradict.
You get a flat pattern, but then
So when I say intensity, I think it means the
again,
baseline,
it's
not the
not because
varying
it's
part.
because it's
Okay.
He specifically said like
Because we separate it into two terms. Right?
two different
But we still have
Yeah.
the two terms in the AC.
like this, and you get the
Still have the
flat line.
two
This
factors
everywhere, right?
in the AC.
It is not because of interference, but it's just like everywhere there is. The light is not interfering, even if it's there overlapping. It's where it says light, but it's not interfering.
So you mean the
usually
one
it's
is
not
interfering?
because it's just
I1
coherence, you
squared
mean,
I.
It's not same frequency.
yeah, not frequency, not
So-
coherence,
so-
everything. No.
You think the first term is interfering?
But here it could be the same frequency, right?
But we are taking two different differences.
Okay, yeah, that argument, yes. Yes, and then you have to.
Or the wave cancelling out interference.
You are taking two different differences. So we are only measuring correlation between the two. There is no interference.
Yeah, I know. Yeah, that's your problem. Now, of course, you need to know that variouts also, but I want to have enough time in lab to understand the results because that's the important part. If you just do a lab and don't have time to like analyze it.
All right, 30 seconds.
The one I
It's just two value added together. No, what if like that? No.
Yeah.
Just number times a number. I think it's not a function.
All right, time's up.
Yeah, but I think you gain knowledge.
Alright. All right, anybody want to switch position? You sure? Okay, let's do a second round of debate. So this time you and Musfa will talk. You will discuss, and you three will be one group.
Right. What did you choose before?
Or you also talking about like we have different detectors. So the light is not
and we are only calculating the correlation between
looking at the signal.
The detectors, yeah.
So there is no difference between the two.
But
No,
in
you
each
read-
detector, we have an inference of
No.
light beams
Or what I say is
from
what
each
I
part
say the
of
intensity is
each side of the
baseline
baseline
of the wave. And there's a
Because
time varying
What is the
function
difference?
that to add it
I think so because you
and when they are interfering together, it's only the time varying parts that will show up on the correlation detector
Oh, I didn't know.
in the end.
But he showed a
The
picture.
intensity
And
and the time varying always cancel out
with
because
detectors, you have the
it's just the
correlation
value
and
times
the correlator.
value
And
times the
that is the
oscillating
part that
signal
is
and average itself is always 0.
comparing the signals.
1 minute.
To detectors.
Just like the
Then
four
between
terms that
each detector
Yeah.
is how the interference path.
this deriving.
We are just taking only one point and saying that one detector.
Then we have the beat clocks.
The clock is like a progression.
Yeah. It doesn't. I mean, it doesn't need two signals.
Yeah, with two different detectors. You have detectors.
Yeah.
We compare that and make the speed clock. We take a correlation.
We normalize it so it goes one.
Okay. But as I saw it, the
But
beat
even if we
beat clock is
normalize-
calculated each detector separately.
And
Okay.
the
That was a difference.
and the beat clock is not like in the prayer. It's like it's two different frequencies.
Yeah.
So they don't interfere with each other.
Okay.
The open lights of different frequency systems.
Mm.
So we just have two different light sources.
Mm.
So if when you take the spectrum, in some detectors we just take this frequency. We have multiple frequency, we have multiple.
Mm.
It doesn't mean these spectrums interfere.
Okay.
I think it's only interfere when it's the same frequency. How would guess that intensity? No, like this doesn't interfere.
It could be.
That shows interference.
All right, hands up.
That
Does everybody? Is there anyone who wants to change answers? Everybody's rooting for no. All right. I think this is a rather puzzling question, and from my standing point of view, I would choose no, because interference for me is phase dependent. So when you change, it's very sensitive to phase. When you change things slightly, you should affect the interference signal a lot. Okay. So in this case, and in the construction of the intensity interferometer, we see only correlation, and correlation is not interference. And if you just change that a little bit, it doesn't fluctuate. So I wouldn't say anything is, at least the intensity is not interfering. I mean, intensity cannot interfere. Okay. yeah, if the intensity, yes, when you see a cross turn, it's easier, it's pretty easy to think of, oh, this is interference. But it is not really the cross turn that matters, it is the phase turn that follows it that matters, right? And the intensity, if this is interference, then the signal, this cross turn should vary with some kind of phase, okay, or kind of some kind of control knob. And in this case, it doesn't. There's no such knob. Okay, so I wouldn't say it's no. So everybody got it right. Okay, so thank you very much. All on the quiz bonus. Congratulations. Let's get to the lab as soon as we can and start this lab.